All right, well, this is a picture of one of those radio towers with the cables going up at various points. It's kind of hard to see, and it's black and white, which makes it harder to see, but I think it's better to draw your own. This just gives you an idea of what you're looking at. So there's one, and there's a couple in Orchard Mesa. They're kind of down, actually, not in Orchard Mesa. It's down by the river, by the zip line. You know, have you seen those, right? With the light on top. And if you've ever driven to Delta, there's that group of 3 of them that are in a row. I've always wanted to climb those. It was really fun.
Let's use them allowed.
Well, I'm not going to go do it, but maybe I'll get permission someday. Anyway, we'll assume that the tower is a right angle to the ground. It doesn't have to be, like meaning maybe it's not, but I think to keep it stable, it's going to try to be. They're going to try to put it up perpendicular. All right. It says 35 meters from the base is this cable coming down. So that's a ground measurement from the base of the tower. And it says the wire makes a 65-degree angle with the ground. How long is the wire? So we're looking for the length of that wire. So pictures could vary, but roughly something like this. Okay? What do you do? We have multiple ways to solve this. Hey, will you shut that door? Do you mind? Thanks.
Right, it was cosine of 65 over equals 35 over x.
All right, so he's proposing that it's okay to do this. First of all, to the 65, 35 is adjacent. Let's label that, and then the x is the hypotenuse. Okay, so first question, is cosine the correct ratio? You guys need to study these. This test is going to kill you if you're not, if this is like shaky. So katoa, A-H, ka, right? So is cosine correct? Yep. Can he do the cosine ratio? Is this an okay problem to do trig ratios on? What is required to be able to do cosine like this?
Or the side length and angle.
Okay, so you're thinking of law of cosines. He's just doing this, the definition of cosine, like the ratio. So is it okay to do? Why? It is a right triangle. So trig ratios work for right triangles. He's good. Okay? Let's finish solving this. So multiply by x on both sides. You'll get x cosine 65. And then divide by cosine of 65. And we'll get 82.8. It doesn't say around or anything, so maybe that's 82.8 meters. Any other ways to do this? I would label this the trig ratio method. Is there another way, though? There is, I'll give you that hint. There is another way to do it. What other ways do we have to do this?
Can we use log sine?
Okay, so let's write out the suggestions. Law of sines. Guys, get your notes out, because if this isn't just coming right to you, then you need to have those notes so you can try to get it there. Because the notes won't help you with this. I mean, they might. Like on the test, when you have 5 or 6 different methods, you have to have some clue where to go. Otherwise, you're going to be reading your notes for the whole test. So, law of sines, he's proposed this. Trig ratios, we already know works. I'm going to write it over here, though, just so we have. Try to write it over here. Get out your notes if you don't have them out. So that one worked. Alright, what else? How else can we solve? This is a length. So how else can we solve for lengths if we have lengths and angles, like just with this kind of stuff? What else did we learn?
Law of sines for angles.
I have that up here. I just put law of sines. But we're solving for a length, so we don't want an
For
angle.
sidelines.
Huh?
Law of sines for sidelines.
Yeah, I have that. I'm just writing it as law of sines. So we'll ask if each of these can be used, but let's at least make a list of what we even could try. What else are there? What else is there? That's this. Well, I don't know. What does it say?
Solving for sidelines of trig ratios.
That's this.
We got this one.
Alright, I'll write law of cosines. Okay, what else?
The other sidelines.
If it's trig ratios, it's already up here.
This one isn't trig though.
Then what is it called?
E times 2 is what it says for mine.
E times 2?
Yeah.
I'm not going to read your notes. I know what they say. I mean, I know what they should say. I can't tell you what yours say. I don't know what E times 2 means. Does it have a title?
Yeah, this is sidelines for right triangles.
So, other ways to solve right triangles, we had 2 other ways that were all just lengths. There was no angles, specifically angles involved. Yeah.
We use angle of elevation.
That's a trig ratio thing.
I don't know if this one would work as probably like that really
Yeah, I mean, we're just right now listing things, okay? So, Pythagorean theorem. And then, what did we learn after Pythagorean theorem? What was it? Well, we just tucked that in there. Probably shouldn't. That was our pre-Uno notes.
Special right triangles.
Yeah, there we go. I'm gonna just put this triangle picture. Guys, look at this. 1, 2, 3, 4, 5 different ways to solve triangles. That's just from this one unit. Before this, we had similarity, where we set up proportions and did the diagonal products. We had congruent solving. I mean, we've done a lot of solving. The similarity thing, we had right triangle similarity, we had angle bisector similarity. We could probably list another 3 or 4 different ways to solve triangles, right? Depending on the nature of the circumstances. So how do you know which one to do? Because you can't just latch on to one of these and always use it, unfortunately. That doesn't work. So let's go through. Is this a special right triangle? Nope. Because there's only 2 of those. What's one of them? Hayden?
45, 45, 90.
Okay, and this is 65, 90, so it's not a 45. What's the other special?
260.
Yeah, so it's not this one. Can we use the Pythagorean theorem to solve for x? Why not?
We don't know the hypotenuse.
Yeah, well, we only know one leg, right? One piece of information is not enough. How about law of cosines? We started this yesterday, so if that's a little shaky, that's okay. But we did get to the point where you could ask if you can use this. Use law of cosines. What do you have to have for it?
Either 3 side lengths or 2 side lengths.
That's in between. So 3 side lengths we definitely don't have. And we only have 1 side length next to an angle, so we don't have enough information. No, 3 angles don't work. You have to have a length somewhere. Because remember, 3 angles could be the same triangle in infinite different sizes. So if we don't have a length, we can't solve for any lengths. No matter what tool we use, we have to have at least 1 length. Anyway, law of cosines is out. Trig ratios worked because it was a 90. It was a right triangle. Okay, now let's ask about law of sines. What has to be true to use it? Yeah. Yeah, an angle, a known angle across from a known side length. Good job. Do we have that? We don't have it directed, but we could get it, right? Because we have this side length. Can we get this angle? What is it? Huh?
Is it 25?
Yeah, it is 25. Let me change the color of that. So 180 minus 90 minus 65. So yeah, law of sines does work. Let's go ahead and solve with it as a review. How do we set up law of sines for this one?
Sine of 25 over 35 equals sine of 90 over x.
Perfect. Okay, so we're going to get 35 sine of 90 equals x sine 25. So sine of 90 is just 1. So x is going to be, I'll write it, but 35 sine 90 over sine of 25. And again, sine of 90 is just 1. So 35 divided by sine of 25. Let's see, 35 divided by sine of 25 is the exact same thing. Okay? So yes, you definitely could have done it that way. But you had to sift, potentially, you had to sift through 5 different ways to get to those 2 ways. If I was going to rank these in order of how often you can use them, I think law of sines would be number 1. Because as long as we know something across from something else, if we know an angle and its opposite side, we can use it. Who cares what the triangle has otherwise? I shouldn't say who cares what the triangle has, because we still would need another piece of information. In other words, I couldn't give you this, like 50 and 10. That's still not enough, even though we have that, because we still need one more piece of information someplace, right? Okay. But mostly it's pretty flexible. Law of sines is. As long as it's right, trig ratios are very flexible, as long as it's a right triangle. And anyway, I want to keep bringing this up because the test will just say here solve, here solve, here solve, and it's not going to say what to use at all. Like it won't say use law of sines, so you've got to know which one to use. Any questions on that? How many of you got it? Either way. Okay. Did anybody get close? All right. Yesterday we did 2 things, 2 big things. One of them we're going to finish today. The other we'll come back to probably tomorrow. So just as a reminder, so it's in your head again. Yesterday we did a applied law of sines problem, finding the height of the tree, and then we did the ceiling, where you had to find some information about the little skinny triangle and then the right triangle that has the actual object in it. And then not forget to add your height like I did yesterday. So 3 parts. Remember that process? Okay, we'll come back to that. And then we started talking about law of cosines, which I'd like to finish and work on today. So Bailey was telling us just a bit ago, law of cosines is good when you have 3 sides or a side between 2 angles. Sorry, I said that backwards. An angle between 2 sides. So side angle side. Then we had this kind of nasty looking thing. What does it look like, at least at the beginning? Yeah, the Pythagorean theorem with this modification at the end, right? And actually it does come from the Pythagorean theorem. So it is somewhat like that. Let's get back into this so we can finish this example. Let me remind you what we were doing. We were solving for an angle. We were given all 3 sides, trying to solve for just one of the random angles. So, is it SSS or SAS? Yes, it was. Write the law of cosines and fill in what you know. But we have to be careful because we only solve for the first or the last part. Like, it doesn't have to be A. It could be X or theta or any other thing. But those are the only 2 places that you can solve. So your variable needs to be one of those. In this case, we're solving for the angle, so it's going to go here. Okay? Then we plugged in the opposite side from x, which was 18. Again, that was another big idea, is the 2 on the ends have to be opposite from each other. The other 2, just like Pythagorean theorem, doesn't matter where you put them, just stick them in 10, 12, 10, 12. Both the same. So we had gotten to the point where we were working through simplifying this, and I said, be careful of order of operations. Because what is it tempting to do right at this last step?
It's like tempting to subtract like 100 and or add 140 or 100 plus 144 and minus 240
Yeah.
at the same time.
It's definitely tempting to subtract right there, isn't it? In fact, even me, like my eye just gets drawn to that, and it feels like, oh hey, those are only 4 apart. I should be able to just subtract and write 4. Why aren't we doing it that way?
The 240 is part of the cosine.
Yeah, it's multiplied right there, so we can't subtract over multiplication. So what do we do instead?
Subtract 244 from
Yeah.
both sides.
So go ahead and work with me again on your notes if you haven't done this already. So instead of multiplying, or excuse me, instead of subtracting on that side, bring this term over. And what are we going to get? 56 plus 60, or plus 24 is 80, I think. Will someone check that?
Yeah, 80.
Now what? We would divide, yep. So we're working to get x by itself, so the next thing to come off is the 240, the negative 240. So we're going to divide that off. And you'll have to tell me this, 80, it's like a third. So 0.333, I think, negative.
Yeah, negative 1.
Okay, last step. How do we undo cosine? Scroll it up. Oh, you mean this way? Is that good for now? How do we undo cosine? Yep, anytime you want to get rid of a cosine, you have to, or any of these trig functions, you have to do the inverse of it. So we're going to say inverse cosine of x. And then do the same to the other side. So inverse cosine, let me clear all that out, of negative 0.3333333. Just stick a bunch in there. And we'll get 109.5. Now there's something called the ambiguous case of both these law of sines and law of cosines that we don't talk about in this at this level. So, what does ambiguous mean? Do you guys know? Just in everyday language? It's a fancy way of saying unclear or not completely understood. Here's, just as a side note, let's go ahead and write this down, and I want you to at least be aware of this. So we're going to say 109.5, and this is an angle, so what needs to go on there? Okay. I'll come back and close that out, but let me just show you an interesting thing real quick. In an obtuse triangle, I want you to think about being able to take, and I wish I could do it like as an animation, but if I took this side do you see how I could swing it? How could I do this? Let me try it with the line tool. Okay. So do you see how I could swing that side over here and make an entirely different triangle with the same side length? And so the reason why we call this an ambiguous case is I want you to notice something. That angle over there doesn't change, and neither does the length of this thing, right? Like it can be there or there and be the same length. So think about law of sines. Also, this side doesn't change. Do you see that? So law of sines would be that angle over this blue length in either case equals this side, and then we have this other weird angle that change. That angle does change from here to here, but because of the nature of the way that triangle can be made in an obtuse triangle, it could be either one. So it's unclear which one it is sometimes. That's called the ambiguous case. And we're not, like I said, we're not going to deal with that in here. So you may never come across that, but what it tells us is that we have to be careful with understanding our result. If that makes sense. Okay? Alright, so that was solving for an angle. That was definitely the harder of the two versions. So most of the work comes in this order of operations process. Be careful there. That's all I want to, that's really what I want to emphasize is be careful with those order of operations. And then also don't forget to undo cosine by doing inverse cosine. Will this ever have tangent or sine in it? No, because it's called what?
Cosine.
Law of cosine. So it'll always be cosine. So this step will always be inverse cosine, not inverse tangent or sine. Would you like an example of how to use this for side length, for solving for A?
Yes.
Okay. Do you guys have a box left?
Yeah, just one more.
I'm just waiting for this to make some more boxes. I could have fit it on that, but I just wrote too big, so give me a second. Alright, so we're solving for a side now. you'll see it's a lot easier than it was with the angle. I guess in the process of writing that, might as well write down triangle. Alright, well, similar to what we did before, make sure you're using the right tool. So is it SSS or SAS? Is it either of those? Which one is it? Side, angle, side, good. And of course, when we're talking about those, we're talking about the parts that we know. So we know the 23, 42, 17. Those are the side, angle, side. And then, if it's yes, you can write down law of cosines. And we're only solving for what in there? Yes, but I'm saying in the formula, what letters can we use this to solve for us? A, yep, little a, and big A. Just those first and last things. Little a, big A. What begins with A? You ever read that book when you were little? Big A, little a, what begins with A? Big B, little b.
I think so.
Yeah, you read that. Okay, and then same as before, fill in or plug in what you know carefully. And I'll just put a reminder here, only solve for first A or last big A. The others has to be, we're going to plug it in as the stuff we know. So what do we know in this one?
C squared is 23.
Okay, well, 23 squared, sure.
B squared is X.
Because that's what we're solving for.
17.
B squared has to be the other thing that we know.
17.
Yeah. Good. Okay, and then we'll write, might as well plug those in over here for B and C. Okay, what else do we know? We know one more thing. I'm going to fill in all the details, but what else do we know?
Small lowercase a would be x squared.
Okay. What else? A is 42, yeah. So we know BC. Let's just make this easy. Whatever sides you're using to solve with, go in for B and C. Okay? You're never going to plug in. Let me not say that wrong. Yeah, I should probably clarify. The extra sides, if you want to call it that, those are B and C. The side opposite of the angle is A, and then angle is big A. So, angle 42, the side opposite of that we're solving for is our X, and then B and C are like the extra sides. Okay? Alright, here's the nice thing. this entire right side is just one big number, right? Like 17 squared, 23 squared, those are both numbers. 2 times 17 times 23, that's a number. Cosine of 42, that's a number. So it's just like one big long thing that makes a single number actually. So if you're very careful, you could type that entire thing into your calculator. If not, then take it in pieces and just be careful putting it in pieces. Okay? But regardless, let's say this becomes 10. Don't write this because I'm just hypothetical right now. Let's say it became 10. How are you going to get x instead of x squared? Square root, okay? So at some point, you have to square root this giant thing. So you can either stick it on and then put all that stuff underneath on your calculator, or you can get a number and then square root. I want to do it that way, where we get the number and then square root. So I'm going to write x squared and then just type all of that into the calculator. In fact, I'm going to write that on here. So 17 squared plus 23 squared minus 2 times 17 times 23 times cosine of 42. Okay, you can just enter it exactly how you see it. And we'll hit enter and get that mess. So 236.8607. And then what did you tell me to do to get rid of the squared? Good. You will have to always do that at some point. You'll have to square root. So on your calculator, you can just hit square root and then go grab that answer, hit enter to drop it down, and hit enter again. So then you get 15.4. So see how much less work that is than the solving for the angle? And it's, I mean, you have to be careful, but you don't have to be as careful. I'll be curious to see if you like law of sines or law of cosines better once you're done. I didn't grab the sheet that we were working on with law of cosines. Excuse me, law of sines. We can hold that one up. It's actually that one. That one. Thanks. Oh, stick it back up. One more time. So guys, the problem, so we know the other ones on this sheet are law of cosines now, right? Which is unfortunate that we took that opportunity to check, but at least get some practice solving with law of cosines, okay? So that would be 2, 3, 6 on the fronts. And then 12 and 13 on that next page. If you finish those, try those challenge problems.